Okay, great. So, Max is here from San Diego, California, but actually spent last year in the Weizmann Institute and got the high-dimensional expander bug, or maybe this is an older result. Okay, you tell us about it.
Yeah, okay, thanks, Avi. Thanks for having me. I don't need a mic or anything. I'm fine for the Zoom. Okay, awesome. Yeah, I'll talk about some work. Actually, it was pre-Weizmann, but proving explicit sum of squares lower bounds from high-dimensional expanders. This is based on joint work with my wonderful collaborator, Ting-Chun or David Lin. I highly recommend working with him if you get the chance. Grab some chalk. So there are a lot of buzzwords in the title, and I want to spend a little bit of time to start just giving sort of a very high-level motivational overview of sum of squares and why you should care enough to pay attention to the rest of the talk. This will be pretty quick, and then we'll actually zoom in on a particular problem and be more concrete for the rest of the talk. Okay, so what is the, maybe I should use this side. Sum of squares, semi-definite programming hierarchy. You know, at the 1,000-foot view, a bird's eye view, this is really some sort of framework for constrained polynomial optimization problems, right? We see this occur in CSPs and things a lot in computer science. So this is some framework for polynomial optimization. You know, think over the hypercube or something like this. In particular, has been realized in the past 20 or so years that this framework is extremely powerful for constraint satisfaction problems, right? Classical things like SAT and XOR. We'll see like a specific, we'll focus actually on XOR today, and we'll go through this all, you know, concretely. And it turns out that sort of conjecturally, a very famous result of Raghavendra is that sort of under the UGC, that sum of squares actually is sort of optimal, you know, gives the best possible approximation factors in polynomial time for any CSP. It's a very powerful framework with respect to these particular, you know, class of problems that captures a lot of what we like to do. Okay, so that doesn't really tell you anything about what the sum of squares hierarchy actually is. So again, still at a fairly high level, we'll actually see like the SDP over here in a minute, but I want you for the purposes of this talk to sort of think of SOS as the following. Of course, you know, I'm brushing things under the rug, but you know, I want you to think of it as sort of a restricted model of computation that, you know, if I'm solving an n variable optimization problem, is sort of broken into n levels that are sort of its computational resource. So sort of as levels, t lies in n, and very roughly speaking, the sort of tth level of the hierarchy gets to sort of look at t variables at once in a very broad sense. Tth level sort of looks at t variables at once, you know, subsets of up to t variables, and as a result, it runs in time like n to the O of t. So if you have some, you know, algorithm in constant levels of sum of squares, it will run in polynomial time, which is why this can be so powerful. It turns out lots of sort of classical algorithms, you know, Goemans-Williamson's famous CSP algorithms, turn out to be captured in constant, even like the first level of this hierarchy. And second, this computational, you know, I'm calling it a computational model, it's also complete. If you go all the way to the nth level, you'll actually get the real solution, the real value of any CSP. It's the system, so, you know, the nth level, I'll say, you know, solves any CSP, but it might run in exponential time, right? If I'm essentially like looking over all possible, you know, variable assignments here, which is 2 to the n time. Okay, so that's the very high level view of SOS, what I sort of want you to have in the back of your head for the rest of the talk. So now I sort of want to be more concrete and talk about a specific problem that hopefully everyone here knows and loves, or at least knows, which is 3 XOR linear equations. So let me, I'll, you know, be very thorough with this one. 3 XOR is like a very standard CSP. We all see in basic complexity. So what is this? An instance of 3 XOR, I'll write as IN, has a set of variables which we'll write. So it has n variables, x1 through xn, and then it has clauses Cj, 1 through m. And in this case, think of m as some like large linear thing in terms of n. So there are like 1,000 n clauses in these instances for our purposes. And what makes this the 3 XOR instance? Well, all of the clauses Cj are these linear equations, right? They have the following form. Cj will be written as, sum of 3 variables, xj1 plus xj2 plus xj3 equals beta j, where this is some value over f2, and these are variables over the q. So we're looking at these equations mod 2 over f2. And okay, so that's the instance of 3 XOR. What's the actual optimization problem here? Right, we want to figure out over all possible assignments to these variables over the cube, what's the maximum fraction of these equations that we can satisfy at once. This is called the value of the instance. And we can also actually write this out, explicitly, right? There's an easy formula for this. This is like the maximum over assignments in the cube. There are a couple ways to write this, but we'll write it like this: half 1 over 2m. I might run out of space here. Over sum over the clauses of just some term that is 1 if the clause is satisfied and -1 if the clause isn't satisfied. Right? And this is like -1 to the beta j, and then -1 to the xj1 plus xj2 plus xj3. Sorry for running out of room there. That's all of the exponent, right? Just 1 if it's satisfied and -1 if it's not satisfied. Okay, I've written this over, in the additive form over 0, 1, because later in the talk, it's going to be useful to have things in sort of this additive form. But if I were to instead write this over plus minus 1 to the n, right, these terms would look like beta j, xj1, xj2, xj3, and this would be a degree 3 polynomial. Right, this becomes exactly a constrained polynomial optimization problem, right, over the cube, which is why it now lends itself to this sum of squares hierarchy. Yeah, also please feel free to stop me at any point with questions. I'm sure that's already implicit. So now I briefly want to actually look at sort of the SDP relaxation of 3 XOR. In sum of squares. I'm not going to harp exactly too much on what the form of this is. I just want to point out a couple salient features that will sort of matter for the rest of the talk. So the first is, I said that it sort of gets to look at t variables at once. What I really meant is that in this SDP relaxation, the actual variables of the program correspond to subsets of variables of the original XOR instance of size up to t. Right? So every subset of up to t variables gets its own sort of vector value relaxation here. And then we're maximizing over some vector value relaxation of the value here, right? Hopefully we can see the correspondence. And this is constraint to some consistency things that comes up from being over plus minus 1. Let's not worry too much about this exact form. So what I really want you to notice here is just that this program is sort of a true relaxation of 3 XOR. In the following sense, if I look at the actual maximum of this program, which I'll write as the SDP value. So I'll write throughout the actual maximum of the program as like the tth SDP value of IN. I claim that it's pretty easy to see that this actually lies between the true value and 1. Right? This is roughly because if I look at an actual solution, I can just plug in some vectorized form of it and I'll get the actual value that corresponds to that solution. On the other hand, there's some normalization or scaling constraint here that says the norm of these vectors is at most 1. So if I just apply Cauchy-Schwarz up here, I'll see that this top thing is bounded by 1. So this SDP value is somewhere between the true value of the instance and 1. And we sort of think that SOS does well, it gives a good approximation if this SDP value is close to the value side. And the instance fools SOS if it's closer to this 1 side. Let me formalize this a little bit. I can finally say what it means for a family of 3 XOR instances to be hard for sum of squares. Right, so we'll say, definition, we'll say that an infinite family, right? Typically when we talk about lower bounds, we don't talk about a single instance which could be hard encoded. We want some infinite family. So a family on, a growing number of variables, in of 3 XOR instances or any CSP, we'll say is maybe not just hard, but hard to approximate. For SOS, can people see over on this board? If there exists a constant mu, a true constant, think of this as like 0.99 or something like that, such that the following 2 properties hold.
Size to write big.
Write big?
Right, for the, I think, a zoom view of it. So.
All right, I'll try to write bigger. Okay, the first property is soundness, which just says that the true value of these instances should be, bounded away from, so the value of, the true value should be at most mu. In other words, you can never satisfy more than like 99% of the clauses. These are really highly unsatisfiable instances. And yet we're going to take sort of the strongest possible form of hardness here. It should have this completeness property that the SDP value should be 1, should be all the way on the other end. That sum of squares cannot distinguish between a fully satisfiable instance, which has true value 1, and these sort of fake hard instances where you can't satisfy more than 99%, or as we'll see, even like half of the clauses at once. Okay. So now we can actually sort of state the main question of this talk, which is like, what problems are hard for SOS? In particular, CSPs.
So now,
Yeah.
here, when you say hard to approximate, basically you have this parameter T, which is something, right?
Right. This will be this is hard for T levels of SOS. Approximate. Yeah.
What to prove it for larger teeth. Yeah.
Right. Yeah. Preferably, this would be the best. We said that n can solve. N is the true value, right? So this clearly this is going to have to be less than n, but we're always going to essentially be aiming. We want T to be like something linear, and that would be asymptotically the best we could possibly hope for. Okay.
And maybe it's worth like pointing that for XOR half is always achievable easily.
Yeah, in 3 XOR, if I just take a random assignments, then every equation is going to be satisfied with probability half. So an expectation, half the equations are satisfiable, and I can always find something that satisfies it. So that's right. In the we're about to see the the version of the theorem for random things, which will achieve this. The best possible mu for 3 XOR is like half plus epsilon. This will change depending on your problem in CSP, but for our specific case, these are the gold standards: theta n and half plus m small epsilon. Yeah, thanks. Okay. So what kind of problems are hard for sum of squares? In fact, there's a very classical answer to this question, which is that random problems are hard for SOS, and in particular, random 3 XOR instances. I guess I could have just slid this board up. Oh well. So this is a really beautiful theorem that was proven originally by Grigoriev and then independently later by Schwannebeck. Says the following. Theorem, Grigoriev, exactly remember the years, Schwannebeck. Sorry, I should draw bigger. Please. And basically, this theorem is that if I take a XOR instance randomly, it will match these optimal parameters. So in other words, if I have, an n variable instance, in, on m random clauses, then with high probability, the following holds. I have soundness. The value of in is going to be at most half plus epsilon, where in truth, epsilon is something scaling with like the number of clauses, right? The more clauses I take, so the tighter bounds I can get on this. And completeness, that the SDP val, the Keith SDP value of in is equal to 1, all the way up to sort of this asymptotically optimal bound, all the way to theta.
It's for m equals O of n.
Yes, yeah, good. I should specify that there is also a type trade-off known for when you have, the number of clauses m depending on it and scaling in certain ways. For the purposes of this talk, m is always like 1000 n. We'll only consider this linear regime. Yeah, the other regime is very interesting, but we don't know how to do it explicitly at the moment. Okay, so this led to a long fruitful line of work, both in hardness of other, optimal hardness of other CSPs, random CSPs, sort of certain semi-de-randomized models, and these density trade-offs and things like this. There's been a lot of work on this. But one thing that until quite recently had essentially completely eluded us was whether you can actually find such an instance. And we've said here, somehow this says that almost all instances are hard for SOS. If I pick a random one, it should be basically optimally hard, and yet somehow actually finding one explicitly, or building a deterministic polynomial time algorithm for generating these hard instances, we had no idea how to do this. And maybe I'll mention that sort of morally, one of the reasons that this is in this regime, why this is harder, is that if you actually have a deterministic instance like this, it has a short proof of unsatisfiability. And I haven't talked about SOS as a proof system, but I won't go into it. But essentially, you have to show that sum of squares does not capture this short deterministic proof, which is in some sense harder than saying it doesn't capture like a Chertoff bound or some random thing, which is what's really going on. Okay.
One quick
Yeah.
comment. So just about the history of the problem, I think this question in the motivation you just asked was first asked by Boaz Barak in 2014.
Oh, okay. I didn't know that.
Yeah, so I just wanted to maybe make that comment.
Okay. Yeah, I didn't know that. All right. We'll write both. Thank you. I actually had no idea where this problem came from.
It seems overperformed list from his 2014 seminar.
I see. Okay. Yeah, I just sort of heard it floating around. In fact, I heard it when I first read this, the paper that I'm about to mention of Dinur, Filmas, Harsha, and Tolsiani, who, to my knowledge, made the first progress on this problem in late 2020, early 2021. And they proved the following theorem, which I'll sort of write up over here so we can compare. Theorem. Filmas, Harsha, Tolsiani. So they prove that there exists explicit family of 3 XOR instances that I'm not going to fully tell you what this means, but we'll know some version by the end of the talk, hopefully. That sits on what are called the Ramanujan complexes, which are sort of the prototypical construction of high-dimensional expanders. That have the following properties. They have this soundness, so the value of each of these instances is at most, some constant like 0.99, and completeness that says the STP value is equal to 1, but only up to square root log n levels of SOS. Okay, so we can compare these two theorems. Clearly we have sort of slight weakenings in both of these components. Let me sort of first mention that this, 0.99 versus half plus epsilon is not such a huge deal, because once you have a constant gap, you can sort of run PCP reductions within the hierarchy, and you can reduce to an instance that has soundness half plus epsilon, only losing like a little bit here in the completeness. So somehow like this is really seemed to be the problem. In the way that this proof went, sort of morally, what DFHT were doing is they were viewing these Ramanujan complexes as sort of folds of an infinite high-dimensional tree, and they were saying like locally, these two objects look, the fold and the infinite object look the same, and so SOS can't distinguish. But this is really only true up to about log n levels. So it wasn't really clear how to get beyond this using HDX or using these types of objects. And moreover, it was sort of realized after this work by Pratt and Tolsiani that this bound is actually worse than brute force search. That you could just brute force search over a bunch of disjoint log n size instances, and by Grigoriev's theorem, you could find one that has even better properties than this. So this, to me, this was sort of qualitatively quite disappointing when I heard it. since this hardness that we sort of thought was coming from this interesting topological structure really was sort of not doing any better or doing worse than you could get from brute force search.
Can you run the arguments of the brute force again?
I think the brute force argument is like you have n over log n instances of size log n, and then you could just like brute force search over log n things and find small set expanders.
You don't even need n over log n. I think the point is that, just imagine a random instance over log n variables. And then it has small values. So you just like run through all of them.
You just enumerate through all of them. Yeah.
So you find one which is small, and log n rounds of SOS wouldn't know that, or like log n over 1000.
Yeah. Good. Okay, so hopefully in the rest of the talk, I will convince you that this is in fact not true. That brute force is not better than this type of interesting high-dimensional structure. You just have to be willing to modify this theorem a little bit. In particular, based on this joint work with David, we proved the following modification. I guess I have lots of different colors of chalk, so I should use them. The Ramanujan complexes will replace with a different type of high-dimensional expanding object that we call a small set high-dimensional expander. These actually end up being derived from quantum codes. And the only other difference is that this is replaced with theta n, basically matching this original hardness of random instances up to the soundness issue. And I guess I should mention that, if you want to talk about other CSPs, there are known deterministic reductions to those. So this actually gives sort of a whole landscape of optimal hardness, at least within sort of the linear density regime of CSPs.
But if you want half plus epsilon in soundness, you don't get one incomplete.
Good. So there are two ways to do this reduction. One of them is to use the noisy hypercube, which loses something in the completeness. The other way is to use the Hadamard code, but this blows up the size of the instance, I think, to like n to the 1 over epsilon. And so now I only have like hardness against big n to the epsilon levels of SOS. It is open, as far as I know, to actually, achieve perfect completeness and half plus epsilon soundness. I think that would be pretty interesting to do. Yeah, great question. Okay, any other questions before I move on? Okay, great.
Does this work for the other hierarchies? Capture other hierarchies up to some loss?
I mean, SOS sort of like is very powerful. So it automatically captures a lot of LP, like Shirali atoms or a lot of these other hierarchies. Proof systems beyond SOS, I don't really know. As far as I know, it doesn't, but most of the basic hierarchies, this will capture. Yeah, this will be hard against. Okay. So my goal now is to sketch a proof of this theorem for you. And really, my actual goal is to convince you that these objects, which I'll define for you basically at the end of the talk, actually arise really naturally when you're trying to de-randomize this original result of Grigoriev and Shonova. And to show you that, I actually have to show you, how this original result worked. So most of the time is going to be showing you this. And then I'm going to show you sort of how to upgrade it to this explicit version. And that will sort of come from trading expansion with high-dimensional expansion.
You can lift the board if you want.
Oh, yeah, let me do that. Thank you. I'm not used to this technology. We don't have that at UCSD.
Yeah, whiteboards you cannot lift.
Yeah. Okay, so that's our goal, which means really we have to look at Grigoriev and Schoenebeck, because that's really where much of the work was already done for us. Okay, so the first thing that I want to show you is that expansion sort of already played a really critical role in this theorem. And to say that, I want to move to what I'll call the graph view of 3XOR CSPs. And this is just a different way to view the 3XOR instances. And it'll come in two parts. I'll have a graph that's sort of encoding the structure of the constraints. And this will be a bipartite graph, where on one side I have variables, the other side I have clauses. So this is like x1 through xn down here, and this is c1 through cm, and cj, which remember was like xj1 plus xj2 plus xj3 equals theta j. This is going to be connected to what you think, right? this guy will get connected to xj1, xj2, and xj3, right? So this is just encoding the clause structure of the CSP. And then, okay, I haven't told you what this beta j is. So there's a second part. So there's also this what I'll call target function, or maybe some people would call it a syndrome. And this is just a 0-1 assignment to the right-hand side of this graph, right? This is some beta and f2 to the c that's telling you the right-hand side of these equations. Okay. And so, how do I generate a random instance now? Well, I just take, I take this graph and I pick a random, 3 edges to the left-hand side for every clause. It generates my random clause. And then I flip a coin for every clause and I, decide this function beta randomly. And it turns out that sort of the two sources of randomness here are really not equivalent in how difficult they are to de-randomize. It turns out that I don't really need this structure to be random. What I actually need is for this to be what's called an expander graph, or some variant of an expander. Okay, so I want to talk about that side of things. So what does it mean to be an expander or a boundary expander, as these things are called? To do this, I'm going to define an operator on here that people call the boundary operator. But this is really just the adjacency matrix of this bipartite graph, mod 2. Right? So what this is I'm mapping functions or sets on clauses to functions or sets on variables, where the value, if I have some function f that's sitting on the right side of this graph, right? The value of delta f at xj2 here is just the mod 2 sum over f on all the clauses that it sits in, right? Formally, this is like delta f, that's the wrong delta, partial f of x is the mod 2 sum over all the neighbors. Okay, that's a little bit, I guess, a little bit of a strange object. So what is this actually encoding? Well, the value of delta f is encoding whether the variable xj sits in an odd number of clauses that are participating in this function, right? If it's hit an odd number of times. And what does that mean? That means if I sum up the clauses, if I were to take all of these xj variables and sum them up, this would be the set of surviving variables. What expansion says, typically we think of sort of expansion means if I have some set here, it has a large boundary. In this version, what that means is that there aren't that many cancellations. Even if I sum, say, half the clauses up, I'm not going to have too many variables canceling. There's still going to be a lot of variables in the resulting sum. So let me now write that a little bit more formally. So we call this graph alpha boundary expander. If for all functions go on this right-hand side, all subsets of clauses, such that f is less than or equal to alpha m, so some linear fraction of the clauses, then I get this size bound that the size of the boundary, the number of non-canceled variables, has to be at least linear in the number of clauses.
Not the same amount.
You could do alpha 1, alpha 2.
You want, okay.
For simplicity,
Yeah.
I'm just going to keep it be the same alpha. Yeah, it doesn't have to be the same alpha. But might as well, up to constants. Just take the minimum. Okay, so in the back of your mind, remember that sort of I said SOS only gets to work with t variables at once. So if we can sort of prove that it has to see many variables through this type of expansion behavior, we're going to get a lower bound against SOS. That's roughly sort of what's going to happen in this group area.
So just to be clear, Max, what is your notion of boundary again?
I think that this is the Hamming weight of delta, the partial f. Yeah, number of ones. So it's exactly the number of non-canceled variables.
This notion of expansion is important for lots of other proof systems before Grigoriev used this for resolution, for
indeed we're going
used in various proofs, and of course it's naturally
we're going to use this for a resolution proof exactly. Okay, I will actually. Okay.
Or if the other one before you.
Oh.
But soon you'll soon be an expert. No, yeah, this is
Practice from.
it's like programming. You move the variable to another register.
Look the other way so you can see it.
Yeah, well, that would have been smart. Sure. Look. All right, so you're telling me this goes up first? I still do it the wrong way?
The function of the clauses,
F is a function on, yeah, it's a 0, 1,
and the boundary is on
the
the,
variables.
so it's a map. The linear map is taking a larger dimension,
Yes.
a smaller dimension.
Yes, which is why you have to have this alpha here, right? This type of expansion can't be true in general, because the right space is larger dimension than the
But
left
if it's like a
space.
lossless expander or unique neighbor.
Yeah, it would be good.
That would.
Lossless is
Yeah.
fine, but unique neighbor
Lossless.
usually says that there is one that you want many unique neighbors.
Yeah, that's right. You need many unique neighbors for this, or odd
Many
odd
odd
neighbors
neighbors, yeah.
in this case.
So we know how to construct these graphs.
Yeah, so this is not the hard part of the problem, right? Yes, exactly. Yes, eventually, I'm going to come to this conclusion that this was not the hard part of the problem. But it will be important to then generalize in the explicit case, because there's going to be some problem that we have to address if we get that far, which I hope we will. Okay, so here's the following theorem due to the same people. That, you know, if the constraint graph G up there is a boundary expander, then this implies completeness versus theta n levels of SOS. And we'll see that this is totally independent of the target function that I pick. This actually does not care about the target function. All that I need is this boundary expansion structure on G.
And the theta n is really alpha. That's it.
I think it might be alpha squared.
Yeah, if you.
Yeah, and in fact, we'll derive that in just a second. Okay, so the proof goes through a different system that was already mentioned. It goes through the XOR resolution system, which is a very, very simple proof system. What does it say? It has axioms that are just linear equations, right? So it has some system, Li equals beta I, and for us, these are just the clauses. So it starts as axioms with the clauses of R3 XOR. And then second, it's allowed to derive, what's the sort of obvious thing you can do here? You can sum the two clauses. You can sum any two clauses. So we can derive, if I have Li equals beta I and Lj equals beta j, I can derive Li plus Lj mod 2 equals beta I plus beta j. Okay, very simple proof system. What's the point? This is going to give me a tool to talk about sort of the complexity of refuting this system, right? One way to show that these clauses were unsatisfiable, that this original system couldn't possibly have a solution, is to somehow sum up these equations in a way where the left side entirely cancels, and I get 0, but the right side sums to 1. Right? I want to find some way to sum up these clauses to reach a contradiction, and we'll sort of talk about the complexity of doing this. Right, so a little bit more formally, this is what's called a refutation. I'm sure many of you are already much more expert in than I am, but let's be thorough. So really, this is a refutation. And what this is a directed acyclic graph, which is probably easier to draw. So the leaves of this, graph are going to be axioms. X3 plus X5 plus X7 equals 0. Okay, so it has sort of lots of leaves, which are the axioms, and then it'll have internal nodes. So maybe I'll write like leaves are axioms, or internal nodes. And the internal nodes just derive, have two children, and they derive the sum of their two children. So in this case, what would this be? X3 and X5 cancel. So this would be X1 plus X7 is equal to 1. These have this thing, and eventually we come up to a root where what has happened? Well, hopefully we've derived 0 equals 1, right? This is the actual contradiction. Maybe I won't write down, everything. Here it should hopefully be clear from this diagram. And what is the complexity of this refutation? Well, it'll be the width. So the width of this refutation is just the maximum number of variables that appears in any internal node. Right? I look through the whole tree and I say, if I went through at some point 100 variables, then the width is at least 100. So this is max number of variables in the DAG, in any internal node in the DAG. And now we can define the actual refutation complexity of our instance, right? Which is just the minimum width over all possible refutations of the instance. So the refutation complexity of IN is just the minimum refutation width, minimum width refutation. Okay, and now I'm going to cheat and use a black box theorem of Schwenebeck, maybe implicitly in Grigoriev as well, that really says this is all that we have to care about. In particular, maybe I'll write it over here. Actually, this version might be due to Tolsiani. It says, if the refutation complexity of IN is greater than or equal to 2t, then this implies that the STP value of the tth level of SOS is 1. So in other words, if we can prove a refutation complexity lower bound, it will transfer to an SOS lower bound, and we can just worry about this sort of very simple summing up structure. Okay. So we've reduced the problem to showing linear refutation width for this system on a boundary expander. It turns out there's a very elegant argument for this that is, I think, essentially due to Ben-Sasson and Rigderson, which is instead of tracking sort of the variables throughout this system, which could cancel and sort of be confusing, we're instead going to track the clauses. And then at some point, we're going to show that sort of many clauses have to occur, and boundary expansion, which says there aren't many cancellations, will mean that many variables had to occur, right? So the idea, Ben-Sasson and Rigderson, I don't remember the year, 01?
Yeah. Roughly when it was a PhD.
Yeah, so track the number of clauses. So how are we going to do that? We're going to define a function on every node of this tree that tracks the clauses. We'll do this inductively by, H of the leaves. It's just going to be the indicator of the clause that the leaf is encoding, right? So this is like 1 of C1, etc. And then the function H on an internal node V is just the sum of the sum of the function on its two children. This is HV left plus HV right. Okay, so hopefully it's sort of clear that as we sum through this tree inductively, this function HV is exactly tracking which clauses are active in the tree. And now we've sort of reduced the problem to the following. If we can find some internal node where the weight of HV lies in between alpha m over 2 and alpha m, I claim we'd be done, right? Because now I can apply boundary expansion, which thankfully I have up there, do this board technology. And this would imply that, delta HV, which we exactly said is the surviving variables in this clause, is greater than or equal to, alpha times HV is greater than or equal to alpha squared HV over 2. That's where the alpha squared ends up coming from. Okay, so very briefly, how do you prove this? And then we'll move to the explicit case, which I probably don't have that much time for, but we'll cover some of. Well, this turns out to be quite easy. We'll define a potential function on each of the nodes to just be the number of clauses, just be the weight of HV, and we'll observe the following 3 properties. First is that the root has large potential. I won't go through this in too much detail, but this just follows from small set expansion, right? This says, from boundary expansion, this says that you can't have short cycles. And this is because, this side sums to 0, but this side doesn't. So this is sort of a non-trivial sum of clauses that sum to 0. But then boundary expansion exactly says this can't happen unless the size of F is greater than alpha M. Right, so the root has to have large potential by boundary expansion, no short cycles. 2 is that the leaves have small potential, right? Kappa leaf. This is equal to 1 by construction, right? The leaves are just axioms. And then 3 is that this potential function is subadditive. Okay, this is less than or equal to kappa v left plus kappa v right. Because I can't sum like 5 and 7 clauses and get 13 clauses, right? This is addition mod 2. It's subadditive. So I start at 1, I end up at greater than alpha M, and I can't sort of more than add. So at some point I have to go between alpha M over 2 and alpha M, which completes the proof for completeness here. Okay, how horribly am I doing on time? Okay, not that.
You have 20 minutes.
Okay, great. Actually, that's perfect. Any questions on this before we move on? Okay, so this sort of tells us, as we saw earlier, this isn't really the hard part of the explicit problem. Indeed, we've had for a long time. Maybe when Grigoriev wrote this, we didn't, but certainly now we have explicit constructions of boundary expanders. So really, the hardness must be coming from this target function, must be coming from soundness. Right? So now we're left with this question: how do we find an unsatisfiable beta? Okay, so one method we talked about, which was you just flip coins, right? You pick beta randomly. And in this case, it should be pretty easy to see that, yeah, you choose this half plus epsilon because, by a Chernoff bound with very high probability, sort of if you fix any solution, it'll satisfy about half the clauses. As long as you take, 1000n or 4n or something clauses, you can then union bound over all possible fixed assignments and get this happens simultaneously with very high probability. Okay, that's sort of the original method that was taken. So what can we do explicitly? Is there any way to actually, give some deterministic algorithm to find this beta? So there's at least one thing that you can do, which is we can drop our standards a little bit. In sort of this definition of hardness that I gave earlier, which is maybe even still up here, yeah, I required that this mu be a true constant, right? That this is something like 0.99, and it doesn't go to 1 as my family goes to infinity, right? And this is sort of true hardness of approximation because it says that SOS isn't giving like a 1 over mu lower bound, a 1 over mu approximation for this problem. So we could instead ask for something weaker, right? We could ask that there isn't necessarily a constant gap between completeness and soundness. Maybe the instance IN is has value less than 1, but it'll be like 1 minus 1 over n or something. So it won't give hardness of approximation, but it'll give some gap between soundness and completeness. And in fact, this has been known for a very long time and is quite easy to do. Maybe I'll wait. Should I lift this board first?
Give you another hour, you do it.
I'll get it eventually. Okay. Actually, I wanted to keep these things. Oh well, I'll just rewrite them. Oh, actually, what I need is this diagram anyway, so that works out. Okay, so here's an idea to do this. What if we can sort of characterize in some explicit way the space of satisfiable beta? Characterize the function, the target functions beta here that actually lead to satisfiable instances. Satisfiable beta. This is actually quite easy, and it can be done linear algebraically. What we're going to look at is the transpose of this operator. Right? We'll look at now at what people call the co-boundary operator, delta, which looks in this direction. Again, it's just the mod 2 transpose of this matrix. So if I have now a function f on the vertices, and I pick a clause Cj, and I want to know delta of Cj, this is just the mod 2 sum over Cj's neighbors. What are Cj's neighbors? They're just xj1, xj2, and xj3, right? That's how we define this. So this is exactly xj1 plus xj2 plus xj3, right? In other words, this is the value of the clause at the particular assignment f. I guess I should have asked them. All right, this is the value of the assignment. And so I claim it, shouldn't be that hard to see that in fact, the space of satisfiable beta is exactly the image of this map, which are called the coboundaries, right? Because anything that's satisfiable, what does that mean? It means that there is a variable assignment that satisfies it. And so there's some pre-image in this. And otherwise, if I pick it to be something in the image, clearly it's satisfiable by that, by whatever I mapped it to, right? So
And if you view it like the Zipf-Stillman codes, what you get is an encoding of the variable assignment. So it's really the classical LDPC code.
yeah. Good. So space of satisfiable beta is the image of delta. If people write this as delta 0. Often this is written as B1, the coboundaries. Okay, so here's an idea. We have linear algebra. F2 to the C is a bigger space in this image because there are more clauses than there are variables. Let's just pick some beta that is, in F2 to the C without the image of delta 0. Okay, we could, for instance, just one of these like indicators for these clauses will work for this, right? So that's fine, but indeed what we might get is exactly some indicator for a clause. And then, think about beta being like, 1C1. And then if I set all of the xj's to be 0, I am indeed going to get some value that looks like 1 minus 1 over n, or something that I can, it's not fully satisfiable, but I can satisfy every clause except, which is the worst possible gap you could get, but it's a gap. Okay, so here's an idea, which really is sort of already implicit in this work of Dinarthel, Harsha, and Tolsiani, which is, what was the problem here? The problem was that in this space, there existed functions which were not in the image of delta 0, but were very close to it, right? There are functions outside of this that are within Hamming distance 1. That was the issue. So what if we could actually sort of find some intermediate space? What if we could find a subspace that I'll call Z1 that sits inside, that sandwiches beta and F to the C and sort of has the following magical property, which probably people who are familiar with codes will recognize, that for all functions F that are in the subspace without sort of this satisfiable beta space, without this image, that all of these should be very, very far from B1, right? That the distance of F from B1 should be, linear, should be linearly far away. And I claim, I won't go through the exact calculation, but it should be pretty hard to see, we said, easy to see. We said that B1 is sort of the space of satisfiable functions. Indeed, if you are alpha far away from the space of satisfiable functions, this means that if I take beta to be my target function, the value of the corresponding instance, in beta, will be, I guess, less than or equal to 1 minus alpha. So that's a simple exercise, and morally, I think it's pretty clear that it should be true. So this sort of gives us some idea, right? Can we find an explicit construction of some sort of subspace sitting between the satisfiable, the image of this delta 0 operator? Say we have an explicit construction of this already. We have boundary expanders. Can we find this subspace sitting in between that has this distance property? And you'll just note that this is basically like saying that the code corresponding to Z1 mod B1 is like a good distance code. Which, as I mentioned, that these eventual objects come from quantum codes, that's the reason for this. Okay, so can we do this? This would solve the problem, right? If we had a small set expander, we'd get completeness by the argument I just told you. And then if we could find this subspace, I could pick something explicitly from it, like Gaussian elimination or whatever. I would pick some beta in Z1 without B1, and I'd get this soundness as well. Okay, so that's sort of our new goal. Except there's a slight problem with this. And to talk about the problem, I want to actually sort of introduce this vector space Z as a high dimensional component of this constraint graph. So I'm going to sort of erase this. So we're now going to have a third part of this constraint graph, which is essentially going to correspond to parity checks. So I can always, given this this is Z1, this is a subspace of this, middle layer, right? As a subspace of F2 to the C. And so I can define that subspace by looking at its orthogonal complement or some set of parity checks, right? Where essentially this subspace Z is going to be all the functions on clauses that sum to 0, over every one of these parity checks. In other words, if I define this mod 2 adjacency matrix this way to be delta 1, I'm defining Z to be the kernel of delta 1. Does that make sense? So I can always do this, for any subspace. I guess I haven't explained why I'm doing it yet. So let me now sort of exhibit what the problem is with finding the subspace Z, where this original graph is a small set expander, or has this boundary expansion property. The problem is that I have this sort of subspace inclusion. Remember what B1 is, right? B1 is the image of this map, and then Z1 is the kernel of this map. But B1 is sitting in Z1, which means if I take a function f and I map it twice, I get 0, right? Because the second map is in the image, and then it maps to the kernel and it goes to 0. So in other words, this tells me that delta 1, delta 0 is equal to 0. Okay, this seems fine. This is something called a chain complex. It's very heavily studied in mathematics. It gives us lots of powerful tools to work with. What's the problem? The problem is that I transpose 0, I get these operators in the other direction. Maybe partial 2 and partial 1. Maybe it should have been 1 and 0, but let's ignore that. Particular, 0 transpose is also 0, right? So I'm also, if I start on this function on parity checks and I map it twice, I get 0 over here. And now this is a problem, because if I look at sort of the boundary, I take a parity check here that say doesn't have that many constraints, or some linear combination that doesn't have many constraints. What I've just shown you is a non-expanding set, right? Because this is in this image, and then this image is in the kernel of here. So this set maps to 0. By the very fact that we could find this subspace, it means that there must exist some sort of canonical family of non-expanding sets that is coming from Z1, that is coming from the parity checks of Z1. Okay, does that make sense? So if there are sort of any small parity checks or small linear combination, we cannot hope for this to be a boundary expander. Just give it sort of counterexamples to this. Okay, and that seems like a problem for this refutation proof up here, right? Because we, somehow very inherently used boundary expansion to track the number of variables that was in this refutation. Okay, but there's sort of one saving grace here, which is the fact that in this version of the proof, this worked for any target function beta, right? This was totally independent of what the target function was. Whereas here, I've picked the target function beta in a very specific way, right? I picked it in Z1 without B1, but forget this for the moment. The important part is that I've picked it to be in this kernel. And what does that mean? Well, that means that when I take any of these boundaries that are giving sort of the canonical non-expanding sets, well, if I then sum beta over these boundaries, I get 0. Right? That's the definition of being in the kernel. I sum to 0 over all of these things. And now I look back at this refutation, when did I actually need to apply small set expansion or boundary expansion? Only when I was summing up to a refutation, only when I was summing to 0 equals 1. So yes, this Z1 has introduced small non-expanding sets, and we can't hope to, in general, have a boundary expander. But maybe this sort of family of boundaries doesn't matter for the problem, right? Because they can't lead to a contradiction. What we're trying to find is the complexity of finding a contradiction. So this, to me, suggests the following sort of natural definition, which is a modification of boundary expansion that says, as long as everything sort of modulo these boundaries continues to expand, then we should be good, right? Because in essence, we should be allowed to ignore non-expansion of boundaries here since they don't lead to refutations. So as long as everything else expands, we should be fine. And this is indeed the notion of small set high dimensional expansion. So I'll say that we're an alpha boundary small set high dimensional expander. Again, if for all functions f over the clause space of sufficiently small size, I can no longer hope for this, right? We just said that sort of Z1 means that there are counterexamples to this. but I can sort of replace it with the next best possible thing. Right? I can say, I can replace this with the distance of f to the image of this operator, the space of sort of canonical non-expanding sets. The image, partial 2, which are the boundaries. Okay. And now I claim if you take this definition instead, and you pick a beta function that is in Z1 without B1, I now claim that you can very easily rerun this entire proof, right? And the only thing that I'm going to change here is I'm going to redefine the potential function, kappa of V, is now going to be the distance of HV to this image. And by this expansion property, you can again show that the root has high potential because expansion mod boundary implies no cycles mod boundary. So this has to be large. We're still summing things mod 2, so it stays subadditive. And all of these axioms are still 1 away from the 0 function, which is distance 1 from the boundary. So we're done. This entire proof went through. If you can show this sort of modified version that I'm calling high dimensional expansion that sort of takes into account these canonical non-expanding boundaries coming from above. Okay, so now all we need is a construction of these objects where the distance, that also have sort of this distance property. And here I'll sort of just state the theorem and tell you roughly where the construction is coming from. Theorem. There exists an explicit family. I'll write sort of these free-term chain complexes as Xn, such that for all functions f in this middle space that have Hamming weight less than or equal to alpha m, so this smallness condition we had over here, the following two properties should hold. One is this boundary distance guarantee. The delta f should be greater than or equal to alpha times the distance of f from the boundaries. I guess it's delta 1. And 2 will actually require this in the other direction as well. It requires sort of a two-sided version of this definition. But also delta 1 of f should be greater than or equal to alpha times distance of f, the image of delta 0. So this is just the same definition, but now looking this way in the graph. And just like we talked about before, how sort of expansion is an upgrade of no short cycles, right? It implies no short cycles. Here, this is like an upgrade of this cosystolic distance version. So this is actually a stronger statement. It implies that you have this distance property and therefore soundness. Okay. And I'm guessing that I'm pretty much hitting the end of my thought. Yeah, I'm exactly it. Well,
can take 5-7 moments.
I mean, all I really wanted to say is that, okay, these exist. And so, running back for the rest of the proof, we're done, right? We've shown that these generate these explicit instances that I think I erased the theorem at some points, but, give you hardness against theta and levels of SOS. Explicitly, how do you actually build these? I'm not going to go into too much detail, but basically the hard work was already done for us. It turns out that sort of what are called QLDPC codes, these quantum low density parity check codes, they are equivalent to having a chain complex like this that has this distance property in both directions. So basically these QLDPCs have no short cycles in both directions. And all you have to do is sort of go through their arguments and upgrade this to expansion. So really we have this stronger sort of isoparametric type behavior that implies no short cycles. And roughly speaking, if people are familiar with these like left-right Cayley graphs that were used in these LTC constructions, the idea is pretty much exactly the same. You have some sort of local, robust or small set expansion structure and global expansion structure, and you sort of piece things together, piece the local small set expansion together with global expansion to get this type of guarantee.
So what do you need is actually top grade. Means this, if you are given the quantum codes that come from the left-right graph, don't they already satisfy this?
Yeah, all that we had to prove was that they satisfy this.
Yeah.
So
The definition of quantum code guarantees to you the first one, right?
No. It guarantees to you just that for all f in it guarantees to you this distance property. It says for all f that is in the cocycles without the coboundaries that the distance is large. This is a weaker statement than actually bounding the size of this. All right, so this implies that in particular. And indeed, it turned out that like if you go through their proofs, they could have proved this if they wanted to. It's not that hard. Instead of analyzing things that are actually cocycles, you analyze things that have alpha m errors, and then that just becomes an extra error term in sort of this Sipser-Spielmann type decoding proof. It's really otherwise the same. Okay, great. So maybe I'll just end by noting this construction that I've told you so far is weakly explicit in the sense that it's constructible in deterministic polynomial time, but to actually find this beta, right, in Z1 without B1, I have to like run Gaussian elimination or do some sort of not strongly explicit procedure. A really nice observation of Dolowich and Kaufman recently is that you can actually construct these sort of QLDPC structures in a way that allows you to plant a target function beta. In particular, you can actually just plant the all ones function. And so you actually get the strongly explicit instances because these left-right Cayley things are coming from like LPS graphs that are strongly explicit. And then now I just, one is very explicit as my target function. So you actually get even strongly explicit instances from this newer work, which is nice. Maybe two other things. One is that it turns out that this property is very important. Maybe this won't be surprising to people here. The stronger expansion property ends up being important for efficiently decoding quantum codes. Just like boundary expansion, I think ends up being useful in decoding like original expander code type constructions. There are a few works that use this. And also it turns out that this property implies the NLTS conjecture, which was true by Anshu Berkman and Nurki after this.
What conjecture?
The no low trivial energy states conjecture. Just some quantum complexity statement about the circuit complexity at I think low or second lowest states. I know very little about quantum.
You want that circuit that describes the ground state. You want a Hamiltonian such that there is no small depth circuit that describes the ground state of a Hamiltonian.
Oh, low depth, you mean constant depth?
Yeah, I think they prove it for slightly super constant, but yes, yeah. I think it was supposed to be like a sanity check for the truth of the quantum PCP conjecture. Like, there should be Hamiltonians for which you actually somehow, cannot certify a ground state in NP. And so you don't want any small classical description. And so small depth is like in some sense, like one special case that you must rule out.
Turns out that you can sort of view these as some type of clustering of code words, things that are even large, or they satisfy this, which helps you prove circuit
The
theorem.
point in the PCP quantum, you want the gap between the energy of the ground state. You are talking about the gap.
So I don't think this goes there. Like right now, I think the NLTS part is simply looking for a explicit quantum Hamiltonian such that you cannot describe the ground state energy efficiently classically. Like you should not be able to describe me a state such that, it has lowest energy.
Yeah.
I'm sorry, the better that you talked about the planted solution.
Yeah.
This is supposed to be like the free coefficients in the Twixor. I mean,
Yes.
how can it be all like the all ones assignment will always be a solution that will give you all ones?
That's true. So maybe it's the modded solution. That's all ones. When we mod by boundary. That's a good point. Okay, maybe I've screwed up what this vector is. I thought it was all ones, but maybe it's all ones in like the modded space. Okay, that's a good point. It clearly can't be all ones. I'll go check what this is. But definitely you can plant some, explicit predetermined vector to get as beta.
Maybe you can do anything that's not in like B1 or something like that.
You have to maintain sort of some symmetry properties for the balanced product to work, which like all one satisfies. But right, you have to be careful that you're not actually a coboundary. which all ones is. So yeah, maybe that isn't modded. Sorry. Yeah, thank you. Good catch.
I guess we are in the questions, yeah.
So what did this previous work on Ramanujan complexes do? Did they just like not identify the correct properties that you needed for this proof?
The Ramanujan complexes don't have these properties. So Ramanujan complexes have short cycles. There are log n size cycles in sort of the downward direction of the Ramanujan complexes. So as far as I know, okay, I won't say you can't from this proof, but it wouldn't work as is. So that
But was it like understood that like these are the properties that you needed and they just like tried to?
their work sort of phrased things a bit differently, but I think it's not that hard to come away with that if you read their paper. Like what they actually did is they used something called Gromov's filling inequality, which is some type of isoparametric inequality that looks sort of like this in sort of the systolic direction. And then but it's not quite like this. It's whatever like actual properties of Ramanujan complexes had. I think that morally their work was.
It's not clear when you're saying their work. I mean, Ramanujan complexes were invented long time before any of the applications existed. The papers of 25 years ago or 20 years ago for Lubotsky, Samuels and Wishman, which constructed them for mathematically elegant way of generalizing Ramanujan graphs to complexes.
I was referring specifically to the previous work on this problem that was.
No, this was unrelated. The applications came much later. There are lots of work on understanding these complexes, giving more definitions of what expansion means. I mean, and starting to find applications in codes and in other things, and trying to get these locally testable codes. But all this came much after the definition of Ramanujan complex. So they have a particular structure, which I think doesn't really answer this. But once it's locally testable codes and quantum local, whatever LDPC codes were developed, these already have, and I guess just property testing or consistency check testing.
Right. Yeah, this is very
Applications came in, all these connections began to be understood.
But I would say that morally, the previous paper, from talking to the authors, I think that their view was really about this.
This was a question about the no, etc.
Yeah.
Oh, sorry. I saw this like Ramanujan. Yeah.
I think that they really viewed things as like the hardness was coming from telling whether you're in the infinite building, affine building object versus the finite modded graph. But like, this is what's going on, right? They prove some isoparametric inequality and they apply it in this way. Like this idea of setting this distance in this proof, it's in their paper. They do some it's not exactly in their paper, but they do this. Really, that's what's happening. I think really you just had to realize that what's going on is sort of this linear algebraic viewpoint, that you don't, like the hardness isn't really coming from this, are you in the infinite object versus the finite object in this case, it's coming from somehow planting Gaussian elimination or planting some linear algebraic problem. But if you go read through their papers, you'll see this. Like, I don't know, when I read the paper, it was like, I sort of thought about it in this way.
I mean, can you imagine your like this construction of saying that there is some infinite object in the background? Like, is there a geometric interpretation, or is this not natural?
I mean, okay, in some sense, like these balanced products are coming, you're modding by some group, and you can try to view this as like SOS can't distinguish between the product space and the balanced product space. I looked at this a bit, but I wasn't able to figure out if this is actually a sensible, like it really seems like it should be a sensible interpretation, because there are lots of these SOS type bounds where you start in some object, even like the hypercube, like there's a sparsest Cutler bound or something where you just mod by a cycle, and then like SOS can't figure out that you've modded by the, or not SOS, but some SDP can't figure out that you've modded by the cycle. So it seems like that should be going on. But I sort of wasn't able to figure out a sensible way to talk about it like that. But it's very plausible that it's no longer sort of infinite building versus finite modded space, but it could be that this this group balanced product maybe there's an interpretation where that's where the hardness is coming from. I'd actually really like that to be true because maybe then we can lift this technique to other types of problems. I don't quite know how to do it in this linear algebraic viewpoint.
Sure. Is there a couple words you can say about this reduction from SOS solution to the resolution proof system?
I don't know the reduction that well.
Oh,
I mean, I think you like run the bounded depth resolution, and it gets you some set of equations that you have to satisfy that you then use to try to define the vectors, but something goes wrong in the consistency constraints, and I don't quite understand what the modification you run is to get things to actually match consistency. I don't know, Pravesh, do you have a good
I don't think in terms of the vectors, I actually feel it's the wrong view. But I think you should think of this assigning, values to monomials. Like, just, so the sum of square system is trying to understand what value should you give to, monomials in the solution space, right? And so some of them are decided for you, namely the 3 XOR equations that you were given to begin with. More are decided for you. For example, anything that you can do in bounded whatever width derivation is also a constant degree, like bounded, what the same degree sum of squares prove that monomial has the given value if you start from some equations. So in some sense, the resolution tells you which monomials have a value in some obvious way, in obvious low degree sum of squares way. And what you say is, okay, this is all there is. Everything else will be set to 0, meaning like, I can't quite determine if they are, plus 1 or minus 1. And what you can show that this is consistent, like, in some sense, there is no low degree violation to it. And the proof more or less is just, expansion.
see. But here, like the width is just talking about like in some sense, the worst case internal width. It's not like you can fully assign everything up to that.
No, so you can think of it as, okay, so when Max defined, the derivation over there, right? Think of like the modifying the step 2 to only doing the step 2 if the monomial that you derive is of width at most some bound R. Okay? So you just don't derive a monomial if you cannot like somehow, get a whatever R size monomial, right? So now, run the system with this constraint. This is like bounded width derivation.
Okay.
And these are all the monomials you will set the value.
Almost all proof complexity results are put this way in all proof systems that we know how to prove low bound.
So it's a weird thing, like, in some sense, the same solution that fools resolution also fools Shriver, Shirley-Adams, and sum of squares. Like they have no power over each other.
Polynomial calculus.
Yeah.
And moreover, in some systems, this width low bound also automatically get you size low bound, which is something you really want. You want to say, a proof of this statement is really long. It's polynomially long, not just that it's closed up. In resolution, for example, a linear low bound on width implies that the size of a resolution proof is exponential. This was really the main point in this paper with Ali.
So Max, one question. So you, I guess you kind of sort of said a sentence about this in the beginning of your talk. What about the dense case? Like, is there a natural object that one could hope to build to get lower bounds when M is superlinear then?
Yeah, so you can get some version of this from the Ramanujan complexes, actually. Basically what you need, right, is some very unbalanced complex, right? Because we need, and what Pravesh is talking about, sort of now there are a superlinear number of clauses, right? And when we looked at this diagram, this means that now this middle layer is way, way, way larger than this variable layer. And so we need, each of these still has like three edges coming this way, but now the degree of this is really high. So like, bounded degree high dimensional expanders, which are the main object of study, won't do this, right? Because
but they are the easy examples. Everybody wants to get a bounded degree high dimensional.
Right.
The original expander and expanders are almost like a complete.
Right. So in some sense. Right. In some sense, it feels like it should be easier. Yeah, exactly. But there's some careful game you have to play because you have to have non-trivial cohomology to get this proof to work, right? Okay, I guess I didn't define those words, but like, this space sort of Z1 mod B1 is called the cohomology. And when you're in a very dense object, this space is just empty. Z1 is just equal to B1 on these complexes. So then like, this is actually one of the reasons you have to use this small set rather than, if I remove this small set requirement, this would just be the definition, the like Grobob's and Mashulon's definition of high dimensional
No,
expansion.
but now you replace it by n to the epsilon, right? I mean, if you have denser, you.
Oh, sure. I just mean that in like typical high dimensional
Yeah,
expansion, you
yeah.
have this, and this would imply trivial cohomology. So that all I mean to say is there's some tension where I have to somehow maintain some non-trivial cohomology in the object, which is like somehow more difficult for dense objects. So there's some weird play here. We do know, I believe, Ramanujan complexes that have non-trivial cohomology, and you can build them in a way that has some density. But I checked this and they weren't like, they don't sort of beat. One of the problems that I've been looking at professionals is sort of trying to build instances that actually beat random. In the case where you have linear clauses, sort of you already achieve theta n, there's nothing to beat. But when you use random instances over a denser number of clauses, you start losing sort of necessarily the number of levels, which isn't necessarily true generically for instances. So you could hope to sort of build these explicit or constructions of these complexes where you specially pick the function beta and you actually do better than the random instances. So you can do this for some of the Ramanujan complexes, but they don't beat the random bound as far as I know. I've looked some with Louis on trying to use sort of balancing techniques from quantum codes to do this. We haven't really had much success.
But you can match random?
I don't think beyond superlinear clause density that I don't think the Ramanujan complexes matches random.
Okay.
I don't think we even know how to match random at the moment. I'm planning to keep thinking about this problem, but I haven't really thought about it since pre-postdoc applications. It's been a while.
More questions? All right, thanks.